In this video, we're going to derive and find the expression for hole concentration in valence band for a semiconductor. Let me take a semiconductor which is represented by energy band diagram like this, where we have conduction band, valence band, where the top edge of the valence band is EV and bottom edge of the conduction band is EC. And the top edge of conduction band is EC top and bottom edge of the valence band is EV bottom. And the difference between this EC and EV is energy band gap, which is also called as forbidden energy gap. Now, our intention in this video is to actually find the concentration of holes in valence band, because the concentration of holes in valence band are the ones which contribute to the conduction of electric current. Now, I'm assuming you have seen the electron concentration derivation video, so that I have to explain a little less in this video. In order to find the hole concentration in the valence band, we need to first find how the energy levels are distributed in this valence band and the probability of these energy states to be empty. If you multiply these two, we basically get the whole concentration in the valence band. Now I'm taking how this energy levels are distributed in valence band is given by a function which is GV of E, which is given by where this function is valid if E is less than or equal to EV. Now let us plot this function where I'm taking in y-axis the energy level E and on x-axis the GV of E. At this energy level EV, we know that GV of E is 0 because EV minus EV is 0. And as we go below EV, the magnitude of this function keeps increasing. And this means that the density of states as we go below EV keeps increasing. Now we know how the energy states are distributed in the valence band. Now we need to find the probability of these energy states to be empty. But we know so far the function which tells us the probability of filling an energy state by electron is given by the Fermi-Dirac distribution. So let me take that, which is given by 1 over 1 plus e power e minus ef over kt. And let me plot that graph where I'm taking e on y-axis and f of e on x-axis. We know that f of e can take values only between 0 to 1. F of E would be something like this, where I'm assuming the Fermi energy level to be somewhere here. F of E basically tells us the probability of an energy state to be filled by an electron, which means we can take 1 minus F of E, which would basically tell us that the energy state is empty, and that's what we're looking for. So I'm writing 1 minus F of E, and I'm trying to plot the same on the same graph where the function would be like this. This is representing 1 minus f of E. This tells us the probability of an energy state to be empty. Now, in order to find the hole concentration in a small given range of dE, we know the density of states in this range of dE, and at the same time we can find the probability of these energy states to be empty is given by 1 minus f of E. In this differential energy range, we can say the hole concentration is dP, which is given by GV of E times 1 minus f of E, which basically tells the probability of the state to be empty, times the differential energy dE. In order to find the total hole concentration in the valence band, we should be taking integration on both sides, so that we have P is equal to integral of GV of E times 1 minus f of E times dE, where the integration limits would be EV bottom to EV. Now if we see this multiplication of these two functions from these graphs, if you multiply, then the resultant curve would be like this, where we are taking E on y-axis and GV of E times 1 minus f of E on x-axis. So above EV, the value of GV of E is 0. So multiplying this with 1 minus f of E would be 0. So till this point of EV, basically the function would be 0. At EV, the value would be 0. And as we go below EV, the multiplication value would keep increasing. And as we go even below, the probability distribution function, the 1 minus f of E, would dominate, and it will drive the value to 0. Now if you see, the area that we have in this curve is actually the total hole concentration that we are looking for. Let me take this constant to be some constant, say C. So we can write this as, after substituting GV of E and 1 minus f of E, this is how the integral looks like. But now the limits that we are going to integrate this EV bottom to EV can be changed, because if we go below EV bottom, pretty much the area under this curve would be 0. So taking it from EV bottom or from minus infinity would be same. So we are going to integrate it from minus infinity to EV. Now rearranging this part of the equation, we can write this integral as this equation. Now in this expression, we can take in the denominator, if EF minus E is, let's say, greater than or equal to 3 kT, then we can say this equation, e power minus of EF minus E over kT, can be very, very small value compared to 1. So we can write this denominator as simply 1. The smallest value that we can have for EF minus E is EF minus EV, because in place of E, we can have a maximum value of EV. If this itself we can ensure that is greater than or equal to 3 kT, we can say our assumption here sticks for the entire range of integration. In that case, let us rewrite this expression, which would be equal to P is equal to this expression. And the assumption that we did over here, EF minus EV greater than or equal to 3 kT, is called the Boltzmann approximation, because the expression here, which is similar form as Boltzmann distribution function. That's why this approximation is called the Boltzmann approximation. Now here on, it becomes a simple mathematical problem to solve. So I'm taking EV minus E over kT as a variable, let's say x, and then I can say dE minus can be written as kT times dx. So which means wherever we have dE, we can substitute this with minus kT times dx. And as E is changing from minus infinity to EV, similarly we can find the limits for x. When we substitute E equals to minus infinity in this, we basically get plus infinity to, when we substitute EV in this, we get 0. So the limits of x would be changing from infinity to 0. We can write EF minus E over kT as this equation, where the second term is actually defined as the variable x. So now taking all these assumptions and relationships, let me write this expression again, which would be equal to infinity to 0 times square root of x times kT, and this would be equal to e power minus of x times e power minus of EF minus EV over kT times minus kT times dx. We can take this minus and reverse the limits. So this would become limits 0 to infinity. So this can be further reduced to c times kT whole power 3 by 2 times e power minus of EF minus EV over kT times the integral, where it is 0 to infinity x power half times e power minus x dx. And we have seen the value for this integral in our previous video, that this is gamma function, and it is gamma of 3 by 2, which is given by square root of pi by 2. So if you substitute this value into this equation, then we would get the whole concentration in the valence band, which will be given by P is equal to C value we know, which is given here, times e power minus of EF minus EV over KT times square root pi by 2. And this can be written as 2 times 2 pi KT mH star divided by h square whole power 3 by 2 times e power minus of EF minus EV over KT. We can take this entire term of constants as n suffix v, representing the effective density of states in a valence band. We have found that this expression is actually given by P is equal to NV times e power minus of EF minus EV over KT, where we said this equation is valid under the condition that EF minus EV is greater than or equal to 3 KT, which we said is Boltzmann approximation. And P, the unit is number of holes per centimeter cube in valence band. So the units on the right side should also be same, and we can say NV units would be the same, number per centimeter cube, and this doesn't have any units. And we also assume that EF minus EV is greater than 3 KT at least, which means this exponential will be far less value compared to 1, which means P will be always far less compared to NV in this Boltzmann approximation. And of course, this equation is valid only under that assumption. We can say that NV is actually the effective density of states, and this exponential basically tells us how much percentage of these states are actually empty, so that it gives us the number of holes in valence band. So that's what it means. This is a very important expression. We'll keep revisiting this expression in future videos.